Most conventional systems work with thread cutters, which does not make any sense, because with bone type 1 we screw the implant into the bone congruent in shape, where we achieve a high level of primary stability. We achieve the highest level of primary stability because with bone type 1 we have the type of bone with the lowest blood supply, the lowest vascularization. So we at SDS say that from a biological standpoint it makes a lot of sense and it's logical to have less insertion torque, while we have higher insertion torque with bone types 2, 3 and 4. This is why our drilling protocol is structured according to bone types. Drill in decreasing order, 4, 3, 2, 1. If you drilled bone type 2 and the implant still has too much torque, remove the implant again, drill again with a drill for bone type 1 and the implant can be inserted very easily. So for every bone type there is a different preparation protocol adapted to the strength of the bone, which is only logical, because if you work steel, hard timber or balsa wood with different types of drills, why shouldn't you do the same in a much more sensitive tissue, such as human bone? Let's now take a look at the drilling protocol. Bone type 4 means that we use a very small countersink to open the cortical bone to avoid any compression or even cause the cortical bone to burst. You can see with all the transparent instruments here, we have compression. The bone condenser has basically been integrated here. Let's move on to bone type 3. The main difference here is that we use the countersink congruent in shape with the upper part of the implant to make sure there will be no compression in the upper part of the bone. There will be compression further down, where it's not delicate, in the cancellous part of the bone. Bone type 2. This is the easiest type of bone. Every implant system works well in this type of bone, so no need to go into the details here. The most difficult and delicate type of bone is type 1, where we hardly have any vascularization. This bone is extremely dense, almost dead. So here it's vital to prepare a buff proportion, as is shown here by the pink shape. You also see here that the outmost edges of the thread just about catch the bone, 0.15 millimeters. You can tell because the last compact drill for the implant has a diameter of 3.8, that's 3.5 for bone type 1. This gives us a difference of 0.3 divided by 2 equals 0.15. The pink surfaces here are all hollow spaces, which means that here the bone is not touched. Even if I were to overheat at the outer edges of the thread, which is a higher risk with ceramic implants, because with ceramic compounds the surface heat remains and cannot be transferred to the core, unlike metal implants, but this cannot really happen here. These are what is known as stem cell lacunae, or bioactive containers, as Ernie Fuchs would have put it.